All right, we're going to try this way of recording where you can see my face as I go through and talk to you about our lesson, which is the intro to the area under a curve. So we've spent some time in calculus talking about slopes, and calculus was really created for two reasons. The first one was to think about the slope of a curve at a point. That we have definitely studied, right? Taking a derivative, finding the slope at one instant or an instantaneous rate of change. And then the other part of calculus involves finding the area underneath a curve. Specifically one that is bound to an axis. So we're going to focus on being bound to the x-axis. Okay, so we're going to have an area that's trapped. So thinking about a couple of these problems, if I had some curve or a function that was just a linear function, we'll call it y equals c, and I wanted to find the area underneath that curve trapped between a and b, I would have a rectangle, which we know how to find the area of because of geometry. If I took a linear, such as the line y equals, we'll say 3x, although that's not a very good representation of it, I could find the area stuck between a and b by using a trapezoid, right? Because it has that nice defined line. But then we start to get into our polynomials, or any sort of curved function. And if I wanted to find the area between, let's say, a and b, now this area, which is well defined, has a very specific answer. There is a numerical answer for that area, but we don't have geometry to help us out. So if we think back to a man by the name of Archimedes, he had the mission of trying to find the area of a circle, which has curved edges, obviously. Well, it has no edges because it's curved. And he started by breaking it up into triangles. So in breaking it up into triangles, he was missing part of the area. All of these little pieces in green, he was missing by finding the area of the triangles. Ideally, he would use an infinite number of triangles, and that would fill the space. So he wanted his triangles to be an infinite amount, and then he could find the area of a circle. So we're going to use a similar method, and we are going to be focusing on rectangles to estimate the area under a curve. So it says find the area of the region under the curve that is defined by the function negative x squared plus 5. That's this function right here. Also bounded by x equals 0. Also bounded by x equals 2. And bounded by y equals 0. So that means we are looking for this green area in here. And as we can see, we've got some linears doing some definition for us, but then we've got this blue curve that's going to create a somewhat of a problem. So it says mathematicians decided to estimate the area of irregular regions using shapes that they already knew, such as rectangles and trapezoids. We're going to focus on rectangles for right now, but we will get to trapezoids later in the school year. So for today, rectangles, 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 area equals base times height. So the first way to think about finding the area underneath this curve, which again we said was trapped here and here, would be to use one rectangle. Then you have to ask yourself, okay, well, what rectangle do I use? Do I do this one? Do I try to create a rectangle down here? How am I going to trap this so that I use just one rectangle? Well, there's something called a left-hand rule. That says if I want to look at one rectangle, I'm going to take the width of my partition. So we have the width of 2. And I'm going to use my left hand. And I'm going to find that height of the rectangle and draw over to the end of my partition. And that will create my area. Well, the area of that rectangle is going to be 2 times 5, which is 10. The other way I could approach this is to say, okay, I've got the area between 0 and 2, and I'm going to use the right hand bound of 2 and cut that one over to create this rectangle here in red. Well, that rectangle has a width of 2 and a height of 1. So using a right-hand rectangle rule, I would have gotten an area of 2. Well, clearly, this green area that we would like to find is definitely less than 10, but it's also definitely greater than 2. So in this case, our left-hand rule is creating an overestimate, and our right-hand rule is creating an underestimate. So I know that the area has to be somewhere between 2 and 10, which is great, but it's really not a close range to know what the area of that curve, underneath that curve, really is. So I can improve my estimation by using 2 rectangles. So again, thinking about how I'm breaking this up from 0 until 2, if I wanted to have 2 rectangles, each width would be equal to 1, because I'm going from 0 to 2, and I want to split that, so I have 2 rectangles. Using a left-hand rule, if I'm looking at this partition, this rectangle, the left hand would be up here at 5, and I'm going to draw over to where that partition ended. Then I'm going to look at this partition. I'm going to go to the left hand on the curve, cut over to where that partition ended. So now I have these 2 rectangles. Using a left-hand rule, I have an area of 1 times 5 plus an area of 1 times 4. So that gives me an approximate area of 9. Using a right-hand rule, if I think about these partitions, and I think about this one and I start with my right hand, there's the height of my function at my right hand, cut over to where my partition ended. I've got that rectangle. This is my next partition. Start with my right hand where the function is, cut over. There's my other rectangle. So this rectangle was a 1 by 1. And this rectangle was a 1 by 4, which means my right-hand rule is giving me an area of 5. Well, this black rectangle definitely has extra area. The red rectangles definitely have area missing. So I know that this green area must be somewhere greater than 5, but less than 9. So I'm closing in my approximation. My right-hand rule is still an under, my left-hand rule is still an over, but I'm getting closer to finding the area of the green that I really want to find. All right, so let's go with 4 rectangles. To save some time, we're going to go with just a right-hand rule, and in fact, a right-hand rule will be our focus as far as our limit summations go. For the AP test, you will need to know how to find left and right by drawing in those rectangles, and we'll practice both with the drawings, but when we actually go through and do the harder calculus stuff, we just focus on the right-hand rule. So if I want 4 rectangles, and I'm going from 0 to 2, and I need to break that up into 4 rectangles, that means each rectangle has a width of 1/2. So here are my partitions. So this is going to be 1 rectangle, 2 rectangle, 3 rectangle, 4 rectangle. Because I'm doing a right-hand rule, I'm going to start with my right hand, right, the right bound, and go to my first partition. I'm going to go up here and draw in this rectangle. The next one then, if I use this green partition, I go to the right hand height of the function and draw over. Now if I look at this one, I'm going to go to my right hand to the function, cross over, and then this very last one will be up here and cross over. So if I want to think about finding the area of each one of these rectangles, I'm going to start with this black one. This black one has a width of 1/2, and its height was determined by plugging in 1/2 into my function. Well, my function was negative x squared plus 5. Then I'm going to add to that the area of this purple one. Well, the purple one still had a width of 1/2. Its height, though, happened from when I plugged in 1 to my function. Moving over to green, still had a width of 1/2. Its height came from plugging in 3/2 to my function. And for the blue one, still have a width of 1/2, but its area or its height came from plugging in 2 to my function. All right, so I just had to edit that video a little bit. So we plugged in 2, but also notice that we plugged in the right-hand value of each one of those rectangles, okay? So looking at this, I can get some estimation using these 4 rectangles, but that estimation would be better if I had 8 rectangles shown here. Probably would be better if I had 16 or 32 or 64. The more rectangles I have, the better the estimate is. So right now, take a second in your calculator and find what this gives us for an estimated sum of the area underneath our curve. Go ahead and pause your video now. Seriously, pause it. Hopefully you came up with 6.25. So let's talk a little bit about how we could write this sum if we had an n number of rectangles. So if I wanted to sum up an n number of rectangles, I would start with one rectangle until n rectangles. The width of each rectangle, we know the area of a rectangle equals the base times the height. The base of each rectangle would be my upper bound minus my lower bound divided by the number of rectangles that I want. So when we had one rectangle, we did 2 minus 0 divided by 1, which was just a width of 2. Then when we did 2 rectangles, it was 2 minus 0 divided by 2, which gave us a width of 1. Here we had 2 minus 0 divided by 4, which gave us our width of 1/2. Then, to find the height of each rectangle, I'm going to take whatever I got, starting at 0, and add the width of each rectangle. 0 was my lower bound, so this first rectangle I added 2 over n times 1. That gave me the black area. Then, to get the purple area, I still had 1/2, but now I went at 0 and I moved out 2 times 1/2. So I started at 0 and I added 2 over n times 2. Then for the green one, that's not green. For the green one, I started at 0 and I got the height by taking 0 plus 2 over n times 3. Okay, so that's where I'm getting those values from. So ideally, if we could, we want to have an infinite number of rectangles. And we're going to write this in a general result. So I would like to sum up from I equals 1 to n, my upper bound minus my lower bound, all over the number of rectangles, because that will tell me the width of each rectangle. To get the height of each rectangle, I'm going to start at whatever my a value was, and then add to it a partition each time. So as I increases, right, as I goes up, we're going to be moving further and further away from that a value, collecting our right-hand values. Ideally, we would like for our n's to get to infinity. This is the right-hand rule, limit summation. All right, so what I'm going to have you do is I'm going to have you stop this video, and we're going to pick up in the next video, just because of time's sake, with an example using this limit definition. So this video kind of builds our area under a curve concept, and then we're going to start actually using this formula to find our exact area under the curve using an infinite number of rectangles.